Hello and welcome to another video. In this one, we're going to be talking about three-way test pollution. We've talked about test pollution a bunch of times before. The short and the long of it is it's some test causes some mutation of global state, which causes some other test to fail. In this video, we're going to be talking about three-way test pollution, where there has to be three things interacting. Somehow, two tests make some sort of modification, and a third test passes or fails based on those three. I guess, hold on, before we get into that, if you want to find other videos about test pollution, I've done a bunch of them. So if you search Anything Writes Code test pollution, I have first, like what is test pollution? This tool that I wrote called Detect Test Pollution, which actually unfortunately has not been very useful for finding three-way pollutions. Detect Test Pollution is really good at finding pairwise pollutions, but not ones of higher magnitude. But yeah, I've been, I've gone over this a few times in other videos, so check those out on my channel. Or if you want to watch a longer stream where I'm fixing those, including the ones that we're going to talk about in this video, you can find those on the VODs channel. Okay, anyway, so to put a little perspective on this is work, so it's work code, so it doesn't make it worse, but it certainly makes it more likely to have test pollution. And I have been trying to basically improve the speed of our test suite, which involves resharding how we run tests. And the tests have run in their current shard order for, I guess, at least a year and a half at this point. And so the particular test order that we have right now works, but when they get reorganized, we tend to run into a bunch of problems, mostly due to test pollution. Things that are actually broken right now, but hidden based on the test order that's currently running. And so I went to debug these particular two, and actually a third failure. There's a third failure way up here that's marked as an R here. And we're going to be looking at all three of these failures and showing how I ended up finding the minimal set of tests that caused them to fail, and then in some cases, tests that caused them to pass. And why my pairwise detector wasn't able to find them very usefully. In order to get started with this, we have all three tabs here. I did a little pre-work, so ignore the output that's already here. We're going to be using this little script that works on files that contain test IDs. This is just kind of the easiest way for me to show this to you. I have a few files, for instance, three-way 1, which has a bunch of test IDs in it. In particular, it has a test ID at the end that is failing. This is the one that I was trying to fix. And then a bunch of either related or unrelated tests. In this case, there are three tests that matter in here and a bunch of others that sort of don't matter, but we'll get into that in a little bit. We also have three-way 2, which I narrowed it down to just 3, so it's a little bit easier to explain. The first one's more complicated. That's why that one's special. And then three-way 3, another set of 3 tests here. So first off, the way that I actually started debugging these was just the same traditional approach that I would use with Detect Test Pollution. First, I would find what revision was checked out here. This A65 whatever. I would go here and then do git check out that. We're already on that, so didn't have to actually change anything here. There's a special target that runs in CI called make test Python CI, which runs this command here. We can actually collect or figure out what test it's going to run by just running the test collection and not actually executing it. So I have a patch, discovery, which adjusts that make target to instead do collect only -q and save that to a test list. This basically collects every single test that would have run in this shard. So, all of these 1,156 tests, I basically can run this. I've already done that beforehand, which generates this long test list here. There is some junk at the bottom that you have to get rid of, but fortunately, we're usually trying to find the last test that failed. So in this particular case, we care about this test, which is actually got a bunch of difficult stuff to type in the journal. But if we do grep this in test list, particularly grep-n, we know that we need the first 1,120 lines in this file, and then we can start trying to bisect down. And that's what I would normally use with Detect Test Pollution. Basically do head-n1120 test list to test list 2, and then I would run detect test pollution with the test IDs file as test list 2, and then the failing test being the last line in test list 2. Of course, I have to put this in double quotes here because that test ID has weird stuff. And this is what I would normally run. Detect test pollution would, do its little diagnostics and then bisect down to eventually find a pair of tests that failed. Unfortunately, when I did this, I got the dreaded, there's a message that's like assertion error, unexpected pass, where it narrows it down to 2 tests and then they're unexpectedly passing. And this is because in this particular case, well, all 3 of these cases I'm going to show you today, it required more than 2 tests. Now, I mentioned that detect test pollution was not useful in finding these 3-way pollutions. This isn't entirely true. I actually modified detect test pollution to be a little bit more helpful, but I don't have a good way to generalize what I've done, so I'm just going to show you the hack that I put into detect test pollution that helped me figure this out, as well as the procedure that I sort of used while modifying the internals. And yeah, normally you don't want to edit files in your virtual environment, but I mean, I wrote this thing and I kind of know what it does, so screw it. There is a particular function here, passed with test list. This is where detect test pollution runs PyTest and figures out whether something is successful or not. I added a little bit of code here to record a last failure. Basically, the last time that detect test pollution ran tests and they did fail, so we somehow have a list of tests which caused the failure, it's just going to write that out to a file. This means that as soon as those 3 tests are no longer in the same chunk, everything will be passing, and the last failed file will have that set of tests. And so in theory, if I happen to split it down the middle and I get lucky and I get the 2 tests plus the last test all into one chunk, then I will be able to narrow it down slowly. Unfortunately, it's not completely automatic, but this was very helpful here. The other thing that I did is what detect test pollution does is it only tests 1/2 of the files. So you're bisecting, in theory, if it's 2 things that you're looking for, you only have to look in 1/2. You don't have to look in the other half. But sometimes it would look in 1/2, it would pass, and it would just assume that the failure is in the other half. But when there's 3 things, that's not necessarily true. And so I had to twiddle these numbers a few times, sometimes just switching part 1 and part 2 so that it found the failing chunk. Okay, a little bit of a hack, but that's not the point of this video. The point of this video is to tell you what are these 3-way pollutions and how do I go about fixing them. So this is how I found them. Eventually I was able to narrow down to some smaller number of tests and then reason about them or narrow them down further manually. But this is how I took it from 1,000 tests to, well, usually I took it from 1,000 to like 30-ish, and then I was manually figuring it out from there. Anyway, so that's the modifications that I did there. Let's talk about the first 3-way pollution, and I think this one is the most interesting one. This is actually one where there's a test pollution that causes a failure, which causes another test pollution as a side effect. So it's kind of like a double pollution at the same time. And again, I think I made up this term test pollution, so a double pollution is another made-up term here, or a 3-way pollution is another made-up term here. And we'll make up another term about a healing pollution here, which is going to be a fun one. But anyway, so I was able to narrow down to this, let's see, how many did I get it down to? 3-way, 1. I narrowed it down to 36 tests. I actually probably could have narrowed it down a little bit further, but this set of 36 tests caused this 3-way pollution. Now, if we run this, I don't know if I commented out the bits in it or not. No, I didn't. Okay, good. I was demoing this to myself before I clicked record so that I would make sure that it actually worked before I tried to record a video. Okay, so when we try and run these tests, I should have done it with -v, but oh well, this will still show the result anyway. S there is skipped, so in fact there are tests in this test list that don't matter. But you'll see here that we actually end up with 2 failures here. This is the failure that I was trying to hunt down, this key error services, and you can see that here in this output here, key error services. This is the test failure I was trying to find. But you'll notice that I actually found another failure at the same time. This produces uptime results in incident test, which if we look up here, There should be a rerun of that, which is a little R here. But I'm not going to find it. Anyway, you'll just have to trust me. So this actually fails the first time, but then when run the second time, it succeeds. And interestingly enough, if I comment out this particular test produces SNUBA result and incident test in this file here, so 3way-1, I find that test. If I comment that test out, interestingly enough, the test should start passing, the one at the end. Now a different test will fail, but we're getting ahead of ourselves here. But the final test will actually pass. This might not be true because it might actually hit the test before it, but we'll see. It should actually pass. Ah, dang it. Well, we don't know. The last dot green? The last dot's green. Okay, so if I commented out that test, now suddenly that last test, we no longer have that key error result here. Peculiar. What's happening here? So the first thing I looked at here is, why is there a system exit? And also, why is it sort of in a random, unrelated chunk of code here? And I noticed the name of this function is handle alarm. Now, what's actually happening here is there is a test at the beginning which calls a piece of code that has a timeout function in it. I actually did a video on this exact topic. If we search Anthony writes code timeout, I actually wrote a video specifically about how to use alarm to make a timeout. So if you want to check out that, search Anthony writes code timeout, and it's video 350. But the idea is there is a thing in signals, import signal.alarm, and this will tell the operating system in 1 second, hit my process with a sig alarm. And if you set a sig alarm handler, you can do stuff based on that timeout happening. The default behavior is for it to terminate the process. It prints alarm clock 14. I believe 14 is the signal here. So basically what's happening is someone had implemented a timeout. They used sig alarm to do this. They had a sig alarm handler that raised system exit 1 by calling sys.exit1. And they forgot to clean up that signal handler and the alarm in their test. And so this was nuking a test from orbit just after a certain amount of time elapsed. So what had to happen is a test ran, it registered the alarm, some amount of time passed, a second test ran, it got nuked at a very particular time in that test, specifically in the setup portion, and then it failed, and then a bunch of other tests run, and then the test that we're trying to fix ran and crashed because the setup didn't get torn down. So that's why there were 3 different things involved here. Now, how did I end up figuring out that this was that important part? A bunch of debugger stuff. And so the actual tricky part here is that test that I commented out. Three-way-1. This test results consumer. Oops, why did that paste weird? What are these weird characters? Where did those come from? That was weird. Test results consumer. What? Did I not? Oh, it's this file, right? Anyway, the test in here, there's eventually some setup that comes from a mixin, which I believe is in this file. Is it this file? No. Anyway, there's a mixin that sets up some state, and unfortunately the teardown never gets called because it got interrupted during setup. And so that partially set up state caused this other test to fail. So how do you go about fixing this? Well, 2 ways. First, just fix the original alarm code, which has already been done. But I also wanted to make sure that this would never fail in the same way before. So I wrote a little bit of code to look for what is going on. Every time I paste, I get these weird characters. Huh. Anyway, anytime a test leaks a signal handler, I wrote a little bit of code here to basically find the leaked signals before and after, and if they are leaked during a test, then it produces a failure. This way, someone else can't make the same mistake by registering an alarm handler and forgetting to turn it off. So if I actually apply this patch, git apply, and then run test vv, we'll see here that this little signal handler catcher is going to fail the test that that was causing the original pollution. So we should see a failure. I believe it's some workflow. Yeah, here we go. It's task worker, test child worker failure task is now erroring because we detected a leaked signal handler here. Okay, so that's the first one, double pollution causing a three-way test pollution. Okay, that was a lot of explanation. Let's talk about a much simpler one, a self-healing test pollution here. So in this case, we have we have 3 test IDs here, 1, 2, and 3. If I run this on its own, I believe it's going to pass. And that's because this is the polluting test, this is the test that fails, and this test causes it to pass. And so this was very, very difficult for me to bisect down, because if I ever had, these 2 tests in one chunk, this would never fail. So I needed to somehow only have this test and this test in order for it to fail. So you can see it's passing here. If we comment out that second test by doing this, we'll see that the test is failing now. And so we actually find a pairwise pollution here, but a third test is causing it to unpollute itself. Yeah, so you can see here now, this test is failing. And of course, if I comment out the first test, it's going to pass as well. I'm going to skip that because you can just trust me on that. And so the question here is, why was this happening? What was causing this to fail in this particular way? And the reason this was failing, 3-way-2, is this test here happens to call an API endpoint in a particular way that sets up a particular global variable. Yes, I know globals are bad. This code was written in 2016, so it, I added the type annotation to it. But there's this special sneaky thread local global variable in Sentry that keeps track of the current request. Basically, somebody was too lazy to pass a long request to some set of functions, so fuck it, global variable. And the actual bit of code that set this up and did it incorrectly is in middleware. It's called env.py. So this was a middleware that captured the request using process request, set it to that global variable, and then was supposed to clean it up using the request finished Django signal. And I learned as part of this that request finished doesn't always get called. And so sometimes this would set it up and never tear it down. And so in this particular case, with that set of tests, the first test would set it up, and then the third test would notice, hey, there's global variables here that I don't expect, and it produces a different output, and then the test would fail. So how would I go about fixing this? Well, the easiest way is to not rely on request finished. So I wrote a little patch that, which one is it? This one. I wrote a little patch that changes that middleware to, instead of using teardown, and I mean, the middleware gets way simpler too. Instead of using teardown, it just uses a function-based middleware and uses a context manager to set that value up and tear it down when it's done. And so this is much less prone to failure than relying on Django signals to do the nonsense. Django signals is kind of like a intentionally global action at a distance system that I find really hard to debug, but also sometimes just doesn't work the way you expect it to. And actually the Django docs recommend doing things this way rather than dealing with request finished anyway. And so it's just following what the docs say. Cool. Okay, so that's a second case. This one I'm sort of calling a healing pollution, because we had a true pairwise pollution, but we had a third test in between which would hide the failure. And we're actually going to show another example of a 3-way healing pollution as well in this 3-way-3. We have 3 test IDs here. This one is the polluting test. This is the one that fails, and this test causes it to mysteriously pass. I'll just show you here. I ran it. They all passed. If I comment out the middle one, 3, comment out the middle one, and we run that again, you'll see that the second test will now fail because the first test breaks it. Now, the question is, why does the first test break this? And this one is actually kind of a funny result in, if we look at the way that this test is implemented. This test uses a hard-coded integer ID, assuming that it will get that particular integer ID from the database and it isn't already populated. And so when it calls create user here, it tries to force that user to have this particular ID. I'll just spoil it. This create project call here also creates a user. And so you might ask, well, okay, I mean, if the database is empty, which the database is empty when you start a Django test, it clears that properly. Why is this a problem? Why is 2 suddenly a problem with this when that other test runs? Well, the database is clear, but that doesn't mean that it always starts from the same ID space. So typically the first test that runs in Django, the first user you're going to create in a database is always going to be user 1. However, I believe Postgres is sort of set up to not reuse that number. So even though the data gets rolled back, the second test runs and this creates user 2, and then this tries to recreate user 2. And so it fails in weird ways because the user already exists. I'm actually surprised that this doesn't hit a primary key conflict and instead just chugs along as if everything is okay. But that's another day. I'll figure that out some other day. And so the reason that this test works if you run another test between those two is suddenly this will get user 3 and then it'll create user 2 behind user 3. And since there's no user 2, it'll work just fine because the auto increment continues to increment. So it's kind of a weird case. I guess my takeaway here is don't hard code IDs. Seems pretty straightforward there. And I think I already merged this one, the fix for that one. Yeah, this one. Maybe I didn't merge it. No, I did. Fix test pollution. Yeah, hard-coded user ID with collide with any test running before it causing the test to fail. So all I did was basically, well, you can ignore that. Remove the hard-coded ID, create the user using the factories, and then use the user's ID rather than hard-coding the value. And so this is another example of a healing pollution where you had 2 pairwise and then another one caused it to pass when it wouldn't have passed. Now, unfortunately, I don't really have a great takeaway on how to find these because I had to do a bunch of manual finagling to figure out how I got these 3 tests in the first place. If you have any ideas for that, maybe I could incorporate them into my detect test pollution tool, but for now, I'm just going to continue to try and find these the difficult way, which is sort of manually bisecting and hope I get them in their own chunks. But anyway, hopefully you found this interesting. If there are additional things you would like me to explain, leave a comment below or reach out to me on the various platforms. But thank you all for watching, and I will see you in the next one.